I'm going to go over some performance measurements, starting with the CPU clock cycle. A computer runs instructions, and an instruction will take one or more cycles to run, and the clock period is the amount of time it takes to do one clock cycle. So in this case, it's 250 picoseconds, or 250 times 10 to the negative 12 seconds. Another way we measure that is with the reciprocal of that, which would be the frequency. That's the number of cycles that the computer will run in 1 second, and it is the inverse reciprocal of the period. So 4 times 10 to the 9th hertz is the reciprocal of 1 of 250 times 10 to the negative 12th seconds. The amount of time it takes to run a program is the clock cycle time, which we just went over, times the number of clock cycles it takes to run that program. Or we can take the number of cycles it takes and divide it by the rate in hertz. So if we want to make our computers run faster, we have to either make it take less clock cycles or run a faster clock. Let's do an example calculation. We have a computer with a 2 gigahertz clock, so it runs 2 times 10 to the 9th cycles per second. If we have a program that runs in 10 seconds, we can figure out how many cycles that is by multiplying the time that it took to run that program times the number of cycles per second to get the number of cycles, canceling out seconds. So this program took 20 times 10 to the 9th cycles. Now say we want to design a new computer and we want it to run that program in 6 seconds. We do it, but it causes more clock cycles. So what is that clock rate of our new computer? So to get the clock rate, we would take the number of cycles, because clock rate is cycles per second, right? So we have to get the number of cycles for the program divided by the amount of time for the program, and we get the clock rate. So the number of cycles, it says it's 20% more, so it's 1.2 times 20 times 10 to the 9th cycles. The program ran in 6 seconds, so it's 24 times 10 to the 9th divided by 6 seconds, which is 4 gigahertz. Another measurement we do is CPI, or clock cycles per instruction. Clock cycles per instruction is, just like we said, it's the number of cycles divided by the number of instructions. So we're going to talk about different kinds of architectures, and there are architectures that run all cycles in run all instructions in one cycle, but there's some that take more than a cycle for some instructions. So what that is dependent on the instruction set architecture and the compiler. And we can get an average cycles per instruction. If there's a collection of different kinds of instructions that take different kinds of cycles, we get an average. Let's do another example calculation with CPI this time. We have 2 computers, one with a cycle time of 250 picoseconds and a cycles per instruction of 2. The other one, as we see here, with a cycle time of 500 picoseconds and a CPI of 1.2. Which is faster? How do you define that? Well, which one runs the program faster? So we have to figure out the running time for each program. And we do that by multiplying the instructions per program times clock cycles per instruction times the seconds per cycle. So that's going to, we cancel out instructions, cancel out cycles, and this is going to tell us, if we multiply the instruction count times the CPI times the cycle time, it's going to give us a number of seconds to run the program. So that's I is the instruction count, 2 is the CPI for A, and 250 is its cycle time. So however many instructions multiplied by 500 picoseconds, that's how long it's going to take computer A to run the program. B is going to be also I times CPI times cycle time. So we do I, number of instructions, 1.2 CPI, and 500 picoseconds for a cycle. So that one will take 600 picoseconds per instruction. So A is indeed faster by 20%. So if we have a number of different kinds of instruction classes that take different numbers of cycles, we sum them all up, get the total number of clock cycles by multiplying the CPI for a particular kind of instruction times how many instructions of that type there are in that program. And we sum up all the different kinds of instructions and their CPI. Then we get a weighted average of CPI by taking that value and dividing it by the total instruction count. Look at another performance measure of MIPS, just millions of instructions per second. And it's the instruction count for a particular program divided by its execution time times 10 to the 6th. It can also be expressed as the clock rate for a computer divided by the CPI times 10 to the 6th. So you have to be careful to use this because different programs can have a different CPI. Different computers can use a different instruction set architecture, and so on. So you can't compare computers with different instruction sets. You can't compare the MIPS of them. And you have to keep in mind that different programs have different collections of instructions, and that's difficult to compare as well. So it's going to vary between programs on the same computer. So just be careful when you're using MIPS. Okay, we're going to do a problem. I'm doing problem 1.7 on page 56. It says, assume that for a program, compiler A results in a dynamic instruction count of 1 times 10 to the 9th and has an execution time of 1.1 seconds. While compiler B results in a dynamic instruction count of 1.2 times 10 to the 9th and has an execution time of 1.5 seconds. Find the average CPI for the program given that the processor has a clock cycle time of 1 nanosecond. So we want CPI, which is equal to the number of cycles per second, so the inverse of the cycle time, times the number of seconds to run the program, times the inverse of the instruction count. So program on the top, instructions on the bottom. So we're going to cancel out program, seconds, and get cycles per instruction. So for A, this would be 1 divided by 1 times 10 to the minus 9 times 1.1 times the inverse of the instruction count, 1 divided by 1 times 10 to the 9th. And that equals 1.1. For B, the CPI would be 1, the inverse of the cycle time, 1 times 10 to the minus 9, times the execution time times the inverse of the instruction count. And that equals 1.25. Let's do part B. Assume the compiled programs run on 2 different processors. If the execution times on the 2 processors are the same, how much faster is the clock of the processor running compiler A's code versus the clock of the processor running compiler B? So that would be the cycle time of B divided by the cycle time of A. That would tell us how much faster A is than B. So we have the time to run a program is in seconds per program, and that equals seconds per cycle times cycles per instruction times number of instructions in the program. So that is, we'll call the seconds per cycle C times CPI times the instruction count. So if they're equal, we're going to have CA times CPI A, instruction count of A equals C of B times CPI B times instruction count of B. So CB or CA equals CPI of A times I of A divided by CPI B times I of B, and that is 1.1 times 1 times 10 to the 9th divided by 1.25 times 1.2 times 10 to the 9th. That is 0.73. So actually cycle B is faster. All right, let's do part C. A new compiler is developed that uses only 6 times 10 to the 8th instructions to run the program. So it compiles it into only 6 times 10 to the 8th instructions. It has a CPI of 1.1. That's pretty darned amazing. Cycles per instruction. It's a pretty cool compiler. What is the speed up using this new compiler versus using A or B on the original? So we want to know what is the time to run C compared to B, and what is the time to run C compared to A from part A. So we have to get TC, which would be, again, the number of seconds for a cycle times the number of cycles per instruction times the number of instructions in the program. So that would be 1 nanosecond times 1.1 times 6 times 10 to the 8th